Let's talk about one of the most fascinating aspects of your brain, its mechanical properties. Now, I'm not talking about how hard or soft it feels, because obviously we don't go around poking our brains, or at least I hope not. I mean the way the brain functions as this intriguing mix of solid and fluid, like a sponge full of water. You see, the brain has to juggle multiple roles. It protects itself with this cushioning elasticity to absorb shocks, like your head bumping into something. But it also needs stiffness. That stiffness helps support the intricate web of connections, the cellular networks, doing, well, their thing, processing everything from, hey, I'm thirsty, to solving your toughest work problems. And here's the kicker. These viscoelastic properties, this balance of solid and fluid, are constantly changing. As we age, for example, the brain becomes softer. This softening isn't just a mechanical quirk. It actually reflects changes in the brain's microstructure. It happens because of things like fewer neurons, or less robust connectivity in the networks that function behind the scenes. On the flip side, certain diseases like multiple sclerosis or Alzheimer's cause mechanical changes too. They disrupt brain networks, leading to softening in some areas, but interestingly, stiffening in others. So how do we even measure something like this in the first place? Here's where magnetic resonance elastography, or MRE, steps in. This innovative technology uses vibrations. Yep, vibrations. To map out the stiffness and softness of your brain in precise detail. It's like a behind-the-scenes health tracker for your brain tissue, showing how diseases or even natural aging impact its mechanical properties. And these changes, they're deeply linked to what's happening in the brain's networks, the cellular players and structures that build its mechanical scaffolding. All right, so let's dive into what actually gives your brain those fascinating mechanical traits. Picture this. You've got four key players working together like a symphony. Neurons, glial cells, the extracellular matrix, and, of course, the vasculature. Each one pulls its weight to shape the brain's stiffness, softness, and fluidity. Let's start with the neuronal network. Neurons are like the conductors of your brain. They transmit signals, connect to neighboring cells, and basically orchestrate everything from thoughts to muscle movements. But here's where it gets really cool. Neurons aren't just fixed players. They adapt. This adaptability, or what you've probably heard of as neuroplasticity, lets neurons rewire their connections in response to new info. It's like adaptive scaffolding that's constantly tuning itself for performance. Then there are the glial cells. If neurons are the conductors, glial cells are the backstage crew, making sure everything runs smoothly. They repair damage, provide energy, and even reinforce the neuronal network, linking it with other parts of the brain's scaffolding. In fact, some glial cells, like astrocytes, form mechanical bridges, connecting neurons to the vasculature. That's teamwork, right? Now, on to the extracellular matrix. Think of it as the setting for this symphony, a molecular web that holds everything together. This matrix houses proteins and fluids, acting like a cushion that absorbs shocks but also enables mobility. It's flexible yet structured, giving the brain its unique blend of softness and elasticity. And what's amazing is that this matrix communicates directly with neurons and glial cells, affecting how they behave and adapt. And lastly, the vasculature. Far from just a plumbing system, it feeds nutrients into the brain while removing waste. Plus, it keeps everything running under the right pressure. When blood flow changes, say, due to stress or a disorder, that mechanical network adjusts too, which can stiffen or soften certain regions of the brain. Incredible, huh? But here's where things can go wrong. When neurological disorders or injuries hit, these networks don't just malfunction on their own. They affect each other. For instance, demyelination in diseases like multiple sclerosis can weaken glial networks, which then disrupt the vascular and extracellular systems. The result? Softer or stiffer areas in the brain, completely altering its functionality. So, let's bring all this together by exploring the practical side of magnetic resonance elastography, or MRE. I mean, understanding the brain's mechanics is fascinating on its own, but the real magic of MRE lies in how it helps us diagnose and even predict brain conditions. It's like peeking into a secret world of how your brain changes with age, disease, or therapy. Take, for instance, brain tumors. By mapping areas of stiffness and fluidity, MRE can highlight where tumors have infiltrated. Cancers in the brain are notorious for softening tissue, but here's the tricky part. They can also stiffen surrounding regions due to swelling or pressure. With MRE, doctors have a tool sensitive enough to detect these mechanical shifts and monitor how a tumor or its treatment is evolving, non-invasively and in real time. Now, that's a game changer. Then there's brain development. Research shows that as children's brains mature, stiffness increases in healthy areas, helping strengthen those critical networks we talked about earlier. What's fascinating is that stronger brain mechanics have even been linked to enhanced memory and learning skills. And with MRE, scientists can actually see this mechanical maturation happening, providing insights into how brains develop and adapt over time. But the impact of MRE doesn't stop there. Imagine tracking how therapies work in real time. For conditions such as multiple sclerosis or Alzheimer's disease, where brain regions often soften due to inflammation or network damage, MRE allows researchers to see whether a given treatment helps restore stiffness or improve network integrity. It shifts the entire paradigm of how we measure treatment effectiveness. What's even more exciting is how this all feeds into the future of neurology. Personalized treatments could be designed to target the mechanical properties of the brain. Let's say a part of your brain needs more elasticity to regain function after an injury. Could we tune therapies to restore that balance? MRE might just be the early step toward making such advanced strategies a reality. And that's really what it all comes down to. Revealing the brain's hidden mechanics to not only understand, but also improve human health in ways we never thought possible. On that note, we'll bring this episode to a close. Thanks for joining me on this dive into brain mechanics and the fascinating technology of magnetic resonance elastography. Until next time, stay curious and take care.